Our first speaker is Konrad Kording. He's a professor at the University of Pennsylvania and co-founder of Neuromatch, a non-profit organization focused on promoting equity in the sciences and advancing open science policies. Konrad is interested in the question of how the brain solves the credit assignment problem, and similarly, how we should assign credit in the real world, that is, through causality. Two of his notable papers for this symposium are Could a Neuroscientist Understand the Microprocessor, and then Causal Mapping of Human Brain Function, which the first one is my favorite and basically influenced me personally a lot. And with that, I'm going to stop sharing and we will mute ourselves here, and then Konrad can take care of the rest. Yeah. Thank you.
Wonderful. I first want to thank the organizers for running such a wonderful, timely workshop. Today, I'll be talking about causal versus non-causal approaches to brain function, and going along with Kaysen's wonderful poster, which was a brain in the shape of a question mark. I checked a little bit just for the fun of it, how far to push the techniques. Here's what happens if I ask DALL-E to draw that for us. The logic of reductionism, it didn't go over all that well. Certain things it's extremely good, certain other things it's not. So let's first talk about the standard framework that people use when they use brains, when they do brain science. Let's call it the standard reductionist dream in neuroscience. So the idea is that we have the brain. It allows us to do certain things. The brain allows us to ride a bicycle. We have that link between what's going on in the brain and the behavior that we have on the outside world. And now let's look at what the logic is of virtually all of neuroscience these days, where we say there is this problem that is being solved, and let's assume that we can divide that problem into multiple pieces, maybe two brain areas. The focus is then on what are the brain areas, or what are the pieces that we're talking about, and what are the interactions between them. And the kind of like logic that people are usually striving for in standard reductionist neuroscience is there's this brain area that tells us how we move through space, which sends that signal to that part of the brain that says, what are the control signals I need to not fall off my bike, which sends it to our muscles, which makes us ride our bicycle. And this logic here, and this logic that we have at that high level, where we say we have brain regions, the brain regions interact, the interactions are the local computation along with the interaction is what gives rise to behavior. That's then something that people are willing to do at all kinds of different levels. Now we can zoom all the way into the brain, and then we can say within that brain, within the brain region, we have a couple of neurons. Now, these neurons, just as previously, now you can say when we talk about brain regions, it's a brain region has a couple of inputs, it does its local computation, it has a couple of outputs. If we zoom in, we can say the same thing for neurons, where a given neuron has a couple of inputs. And by the way, both the brain and the neurons here, they all come from DALL-E. I was just, for the sake of making the talk fun, I was trying to get as many of my graphs as possible from DALL-E. And but the idea here is now every neuron we can view as a unit. It has a couple of inputs. It has one output if we talk about neurons, or a small number of outputs. And then there's some computation happening in between them. And so on and so forth. Now we can say that same logic that we say, what are the pieces? What is each piece doing? How the other pieces wired together is something that we can see at all areas. And that is standard. That this basic idea is the bedrock that neuroscience is built on. So let's zoom a little bit into the logic, and you will see in a moment why I'm pushing on that logic, because there's a lot of assumptions that go into it, and there's implications for how we should be doing neuroscience. Now, the first assumption is that the pieces can meaningfully be understood individually. Now, if the brain area can, for the standard framework of systems neuroscience to add all work, We must be able to kind of say, okay, there's inputs and there's something we can understand about the inputs. And then there's a local computation and then there's outputs. And we must be able to sort of look at that in separation from the rest. So the pieces must be, it must be possible to understand the pieces individually. And most of this stuff needs to, in a way, happen on the individual piece. The second one is this, there's an implicit assumptions about the interactions being simple. Like if the interactions between different pieces are very complicated, and then that whole idea can't work. So it really has the strong assumption that most of the things must happen on the piece, and that we can sort of compactly describe how each piece talks with each other piece. No? I have a USB-C cable here that powers my computer, and this USB-C cable is very simple relative to what happens within my computer. And therefore, it makes a lot of sense for me to describe the USB cable and to describe the computer independently and to describe my power supply in yet another different way. And the pieces themselves must be simple, no? Because otherwise, we couldn't meaningfully understand it, and the whole framework would run into problems. And there's experimental demands that come with this way of thinking. We must have ways of separating computation. We are looking, we're always, when we do neuroscience experiments in the reductionist framework, we are looking for ways where we can say, here's a computation that's entirely separated from the rest. So we build experiments where everything is very easy up to this one place. Like I show you dots that move left and that move right. There's nothing interesting in the stimulus. The only place where it's interesting is this little piece where integration happens. And much of neuroscience is an art of finding these things where we feel that we can argue that it is a separate computation, a computation that we expect to be happening on one of our puzzle pieces or one of our brain regions, or one individual neurons, maybe if we're talking about C. elegans or Drosophila. So, and for each piece, the inputs must be known, and we need experimental techniques that tell us what the inputs are, and we need to analyze what the local computations are. All of these assumptions are always assumed. Virtually every experiment assumes that. They're never tested. And let me highlight what I mean with that. So for us to meaningfully ask the questions we ask, like what does V4 do or something, we need to assume that there's a localization, that stuff happens in that brain region. And do we know that? Do we test that it happens within that area? No, there's no experiments that could possibly help us, possibly really test that this is happening within V4. The only thing we do is we stick electrodes into a small number of other places. And if we don't find the signal so strong there, we like imply that it's happening in one area. We also assume that we also need to assume that the inputs are known. Like this area gets this kind of a code as an input. Like V1 gets LGN as an input. Like guess what? V1 also gets inputs from V4 and lots of other brain areas. But we assume that it's basically approximated by the LGN type input that goes into it. Always assumes, every theory assumes it, the experiments assume it. If you read the Ubel and Wiesel paper, it assumes it. It's never tested. And the idea that we can test local computation, that they're in a way localizable, always assumed, never tested. So you see a framework there. But on top of that, there are also all causal problems. Like what's the questions that come with that framework? How do the inputs to a piece affect the outputs of that piece? How do the outputs of one piece affect the inputs of the other? How do the components on a piece affect one another, producing local computation that defines the input-output region of the piece that we're looking at? All these questions are causal questions. And that is why for the last couple of years, I've been very much obsessing about the nature of causality and how we can learn about it. So you will see if you look into the neuroscience literature that that we don't know all that much about like actual causal questions there. Why is that? Well, For a long time, perturbing is fundamentally hard. It's much easier to record from somewhere, say put someone into an fMRI scanner, than to perturb them, say zap their brain with the TMS system. On top of that, the perturbation methods that we use are universally low dimensional. Like I can put a magnet over your head and zip, but that's one dimensional. I can't do 1,000 dimensions. I can't have 1,000 of them everywhere. If you look at other techniques like optogenetics, light versus not light, it's a low dimensional way of doing things. It's also optogenetics tends to be non-local, so there's fundamental reasons for that. And our observational approaches that we usually use, think fMRI with functional connectivity techniques, they're hopelessly confounded. And that's what I will talk about in the next couple of slides. And even if they were not confounded, we'd still be underpowered to find out about the causal interactions. And I will probably not have time to talk about that because I will wrap up at exactly 9:30. But there's problems there. So let's talk about the problem of confounding. Like we have two things, two pieces, two variables that we measure. We want to find out how does one affect the other. That could be all very easy if this is how the world will look like, but unfortunately, there's always that background thing. And let's be clear that we share an idea of how big that background is. I record from two brain areas or two neurons. Those are one-dimensional signals. How much confounding is there? Well, the brain has 10 to the 11 neurons. So there's like 10 to the 11 minus 2 confounders if we have a setting like that. So the number of confounders is huge. And often people don't see the confounders. They're like, yeah, but we record from the whole brain. But that's not the case, because within that brain region that we might be recording from with the technique, there are many, many dimensions that unfold in parallel within that region. So there's a continuum of confounding. There's areas where there's no confounding. Let's say Atari game playing, ImageNet, and so Go, chess, and like it's fully observable. There's cases with a few of them, like StarCraft. This is where state-of-the-art of machine learning is. There's areas where there's countless confounders, like medicine. This is an area where machine learning profoundly underperforms. So in medicine, you have press releases on machine learning being useful all the time, and you have virtually no applications in the real world there. And then there's the brain, 10 to the 11. So I want to build some intuition about the nature of confounding. And I think that that's much more interesting than, say, pushing towards complex models, which is what much of my job otherwise is. So, and that intuition building, I will be using a couple of slides from Neuromatch Academy. And the ultimate way of learning about that is playing with it. So if you think that there's ways how you can understand and interacting systems of maybe thousands of neurons, well, I give power to you. That's wonderful. And it's super easy for you to convince yourself if you can or not. You just go to these Neuromatch Academy tutorials and you build in which assumptions about the real world, about the brain you're willing to make. And then you can see if you can actually reverse engineer it. So let's look at it. Let's start with the simplest possible system. And it's a great intuition builder. And I'm still wrong at my intuitions about this super simple system. It's a dynamical system where we say the state of the brain at a given point of time is a nonlinear function sigma. You can take that away. It doesn't really matter. Times, and then we have matrix A times the previous time step activities plus some Gaussian noise. So X here is an n-dimensional vector, and it represents, say, n neurons. It could represent n brain regions if that's what you're into. And now A is an n by n causal ground truth connectivity matrix. And so A is how causality really runs. And then we have some noise, and we initialize it to 0, and we are looking for... and what do we expect? If we have such a system, we expect the relationship of neural activities at one point of time to relate to those neural activities at the next point of time. And so you would expect the time delay one correlations to be a good approximation of causality. Like if a neuron is active at time t, and then it systematically activates another neuron at time t plus 1, we should have lots of cases where one neuron is active and then the other neuron is active. So we expect the time delay one correlations to be close to causality. And this kind of logic is in a lot of analyses of, say, functional connectivity in neuroscience. There's cases where you use time, there's cases where you don't use time, but they all have a flavor very much like that. And all the mathematical things I talk about like carry over to virtually all the others. No, this is just for intuition building here, but like the problems that we will see here will basically exist for all other systems. Okay, so let's do that. So on the top thing here, we have the connectivity matrix. If you want, that is causal ground truth. That's how the pieces, in this case, neurons, actually influence one another, okay? And we chose it so that it's a sparse matrix because that allows visualizing things. And now that time delay one matrix, you can see is almost the same. Okay, wonderful correlations, causation. Konrad can go home. All ideas, all this causality talk that's happening in neuroscience, we don't need it. No, but that's not the case. So because if we take that same system that we simulated like that, and we just go from 6 neurons, as we have here, to 100 neurons. The cool thing about 6 neurons is Konrad can kind of simulate the 6 neuron system in his head. And that is where our intuition is. So in our human intuition, correlation and causation are very similar because these small systems that we think of, in those small systems, correlation is like causation unless we maliciously design them. So now let's go to a high dimensional system. So here we have 100 by 100 connectivity matrix, and now we have the time delay one correlation matrix, and there's absolutely no similarity between the two of them. So what's happening here? As we go to large systems, they're starting to have their own dynamics, their own activities. These dynamics now dominate what's happening, whereas the little noise that we inject starts being progressively irrelevant. So because of that nature, the matrix that we get looks very, very different. In other words, correlation is causation in very small systems, and it gets to be very different from causation as we go into very large systems. Brains are very large system. Now we are talking about a 10 to the 11 dimensional system. It gets to be very complicated. Our intuitions about causation are fundamentally misguided then. And here's the analysis. So what I just showed you anecdotally, here's how it looks like if we actually do that. We take the number of neurons, we change that number, and we progressively see that this correlation gets to be worse. Now, there's a lot of people in neuroscience who say they can give you causation from observation. It's an industry. They use titles like functional connectivity and effective connectivity. Which view is the right view is something that you can answer, that no one can answer for you, but I can highly recommend just go to like these Neuromatch simulations, simulate a system that you can actually believe in, and test if it actually gives you correct causality. And now, is that problem fixable that I told you about? Sure, it's fixable. For example, if you record from all neurons in the brain at the same time, it's fixable. It comes from, there exist confounders, neurons that you don't record from, but that play a role that you didn't record from. And so you could fit a model where all neurons are part of it, and then the problem should, in principle, go away. Now, but in reality, we would usually not record from all neurons or all open dimensions. If we will always record a small number. In reality, we will maybe record 30,000 brain regions out of the 10 to the 11 dimensional system. Or we might record from, if you've seen Neuralink presentation 2 days ago, they still only record from a couple hundred. coming up a good number of thousands, but they're still tiny relative to the 10 to the 11. So what do we have there? As the number of neurons that we record from goes down, we progressively get worse. Correlation becomes again different from causation. If we record all of them, we can basically correct for what all the other neurons are doing. But you can see we get rather bad as we lower that number of recorded neurons. So why is this a problem? So let's briefly get the mathematical idea. When we do linear regression, which is what we'd be doing here, all the advanced techniques are basically souped up versions of regression and inherit virtually all aspects of basic regression. When we have regression is we take the X prime X matrix, that's the autocorrelation matrix, we invert it, and then we multiply it with the correlation matrix. X and Y here would be could be activity at time t versus activity at time t plus 1 versus the activity of another neuron at t plus 1, or it could be something same time. There's lots of versions of that, but they all produce equations that very much look like that. So that's our estimate of the interactions, if you want, if we do linear regression. But now imagine we're in that situation where the activity, where the output Y is a part of the causal system that we do understand and record from, or that we do record from, xi beta, and that there's another part that we don't know about, which is zi delta, and then there's noise on that. Now we can take that equation and we can put it into our estimation equation. And then what do we get? We get that the expected value of my estimate is the true one. That's good news. No, like at some level we'd be at the right one. And then there's a bias. And that bias has the same form as the original signal. And importantly, this bias, every one bias term, should be, in the way we set this up, of the same order of magnitude as the actual causal effects. Now, why is this a problem? The reason why this is a problem is it doesn't go away as we go towards larger data sets. So a lot of people, if I tell them, well, like, look, the functional connectivity technique's hopelessly confounded, they're like, okay, how many more subjects do we need to go? No, this is something that happens in the limit of an infinite amount of data. So in the perfect situation, it will still never go away. And also to get you an intuition of how bad this bias is. So beta is of the size of how many dimensions we recorded from. But that bias term that we have on the right-hand side is proportional to all the dimensions that are relevant that we didn't record from. And we are never recording more than an absolutely tiny subset of the relevant dimensions. And that's why there's a bias that fundamentally makes it impossible to get at causation if we have only a very partially observed system. And yes, so far have I argued that we cannot get at causality. And I should say there's another extra story that I recently added, which is, imagine you could record every neuron in the entire brain, from the birth of the animal until it dies. Even then, it might not be possible to be statistically powered to identify what a neuron does. But so altogether, these stories, they tell a story where basically we cannot get at causality. But let me now make the point for why we shouldn't even trying to get at that. Now, there's many flavors of understanding that we could aim for. We might want to know some truths about brains. That's easy. We might need abilities to fix brains, which matters if we are medical, if we work in the medical profession. But in that case, if we look at what actually happens, most of the things that are useful are people just try the dimension that they can do something about, and then they see which things work. We might want to predict brains or be able to simulate it. For predicting or simulation, we would really want to have a causal network that allows us to simulate it. And ultimately, we might want to understand how it works. So, but let's talk about complexity a little bit. Like the whole approach of reductionist neuroscience is based on finding simplicity somewhere. And I argue that there can't be simplicity. Think about Tic Tac Toe. You probably all know how to play it without ever losing to it. There's 255,000 different games you could play. And the perfect rule to never lose, you can summarize as this: win if you can, don't lose if you can't, take the middle otherwise, take the corner otherwise, play with this order, you will never lose in tic-tac-toe. So it's a fundamentally compressible thing. Now let's take the game of Go. And the game of Go, that didn't work all that well. In fact, if you go to Amazon, you can find countless books that tell you that that pretend that they teach you how to play Go. And yet, if you can read all those books, and you will still be very, very mediocre at playing Go. So in other words, Go might not be something that has a compact description where you could say there's a concept like thickness that a lot of people talk about that's real. But the number 1 million of the rules best at describing Go might still be important and describe something. They're all real. And you could say, if neuroscience is more like Go, we can write so the question is, how much variance is in the tail? There's a small number of things that I can tell you about. Lateral inhibition, I can give you principles in neuroscience. The question is, if the principles as we write them, if they will ever describe the bulk of what happens on the computational side. And I want to make the analogy here to neural networks there. Neural networks, we use PyTorch code to design them, and after we train them, we can use the weight dump. Now, we looked at neural networks using a technique called distillation to see how much information we need so that we are good. And if we do that, we generally find that we need a crazy number of parameters that we could never get. Now, where's the information coming from that's stored in our brains and in our neural networks? Well, arguably, we might soak up some 10 bits per second from the brain. A year has pi times 10 to the 7 seconds. We live 30 years until we are like PhDs, until we are postdocs or professors. So therefore, our brain at that point of time contains 10 to the 10 bits. This is something that a human being could never understand. So that causal system, if we could identify it, cannot be of the nature that we can summarize it. And relative to the information that we soak up from the world, the information in our DNA is very small. So at best, we can hope that there's some guiding principles that we could learn about. Now, causation is incredibly complicated and distributed, and even if we had it, there could not be a compact description. So alternatively, we can ask for generators of causal systems. The argument is basically, if we had the part PyTorch for the code for the way human brains are made, that might be small. The resulting network after learning might be arbitrarily complicated. So let's try to do the first thing. Trying to understand computation per se might not be possible. In other words, don't study the brain, study the process that makes the brain. What is the right language for that? We can talk about architectures, we can talk about objective functions, we can talk about optimizers. And in all that space, there's a fundamental criterion, which is efficiency. So now, let me do one last zoom out here. In machine learning, we basically have one big principle that describes everything happening there, and it might very well generalize to brains, where you can say, what do we need? We need a big system that's heterogeneous and can efficiently implement the right functions. What should we do in the real world? Well, take the parameters of that system, have a way of moving each parameter into the right direction, and repeat that. And that's so basically just optimize in parallel along lots of dimensions, and that tends to work surprisingly well. Now, it is 9:30, so that brings me to my take-home message. So I think that the causal reductionist framework is conceptually weak. It's unclear what we want from it. It's experimentally currently infeasible. because we can't make the causal statements that we want. And even if it was feasible, and I could write down for you the interaction in the brain, everything against everything else, even then we couldn't understand what we'd be getting out of that. So I think we need to reframe the problem and rather ask how learning works. PyTorch code can make an artificial neural network easy to understand. I would hope that something similar can work for the brain, and the resulting network is almost guaranteed to not be understandable. So let's do an analog of this, looking for learning in neuroscience. And I want to thank all of you for your attention.
Thank you.